Welcome to the deep dive.
Yeah.
Imagine the entire planet running a low-grade fever. That's basically what's happening.
Yeah.
Since the Industrial Revolution, Earth's average temperature has spiked by almost 1.5 degrees Celsius. And get this, 2024 apparently shattered records at a staggering plus 1.60 degrees.
It's a truly stark figure. Really highlights the immense stakes we're talking about today.
Absolutely. So today we're taking a deep dive into this really complex, really critical topic of climate change.
Mm-hmm.
And we want to put a special focus on the global phenomenon of sea level rise and, what it actually means for us, for human society.
Right. And for this, we've pulled from a few key places. There's a pretty comprehensive Wikipedia article on climate change itself.
Okay.
Then a detailed review from PubMed Central that focuses just on sea level rise.
Right.
And of course, we've got the latest updates from the IPCC woven in there too.
Great. So our mission today is basically to unpack the science behind all this, understand the impacts, what's happening now, what might happen later, and also explore the solutions being pursued around the world. We really want to help you become better informed about this incredibly pressing issue.
Definitely.
Okay, let's unpack this.
Let's do it.
So before we really get into the deep implications, maybe we should clarify some terms. Because you hear global warming and climate change thrown around a lot, sometimes, together.
Yeah, interchangeably.
Exactly. But scientifically, they're not quite the same thing, are they? What's the key difference we should keep in mind?
That's a really good place to start. So global warming, that refers specifically to the increase in the global average temperature. Think of it like the planet's fever reading going up. That's the core symptom.
Okay, just the temperature.
Just the temperature rise, yeah. Now, climate change is much broader. It's the umbrella term. It includes global warming, yes, but also all the other effects that warming has on the Earth's climate system.
Like what kind of effects?
Well, like changes in rainfall patterns, more frequent extreme weather events, maybe shifts in ocean currents, melting ice. All of that falls under climate change. So, yeah, well, people often use them interchangeably. Scientifically, they do have these distinct meanings.
Gotcha. And the sources seem really clear that the current warming, this isn't just, a natural blip. There's a strong human fingerprint here.
Oh, absolutely. The overwhelming scientific consensus is that the current warming trend is driven by human activities. Primarily the massive burning of fossil fuels, coal, oil, gas that really took off with the Industrial Revolution. And alongside that, you have things like widespread deforestation, certain agricultural practices, industrial processes. They all release greenhouse gases.
And the main one is carbon dioxide,
CO2 is the primary one, yeah. It's the most significant driver.
So just how much has CO2 increased?
Yeah.
Like compared to before we started burning all this stuff?
It's gone up by about 50%, since the pre-industrial era. Yeah, and that puts atmospheric CO2 concentrations at levels not seen for potentially millions of years. It really underscores the scale of our impact.
Okay, but people sometimes say, well, the Earth's climate has always changed. We've had ice ages, we've had warmer periods. How do we know this time is different, that it's not just another natural cycle?
That's a fair question, and you're right. The Earth's climate has always fluctuated naturally. We know about periods like the last interglacial, maybe 125,000 years ago. Temperatures then were maybe 0.5 to 1.5 degrees Celsius warmer than pre-industrial levels.
And sea levels were much higher then too, right?
Much higher, maybe 5 to 10 meters higher than today. And then you have the ice ages, obviously much colder.
Okay.
But here's the key thing. Despite that natural variability, if you look at the average temperature trends over, say, 20-year blocks since the Industrial Revolution started, you see this clear, progressive, human-driven influence that really stands out.
So it's the speed, the rate of change.
Exactly. The rate of warming we're experiencing now is just unprecedented in, well, at least the last couple of thousand years, likely much longer. It's happening much faster than most natural shifts.
I found this really interesting bit in the sources about a period roughly between like the 18th century and 1970 where there wasn't much net warming. It almost looked like things leveled off for a bit.
Yeah.
Why was that?
Yeah, that's a fascinating period. It really shows how different factors can interact. So during that time, the warming effect from the increasing greenhouse gases was actually being kind of masked or offset.
Masked by what?
By the cooling effect of sulfur dioxide emissions. Back then, especially with coal burning without much pollution control, we were pumping out loads of sulfur dioxide.
Okay.
This created tiny particles in the atmosphere aerosols that actually reflect sunlight back into space. It's sometimes called global dimming.
So CO2 was trying to warm things up, but this sulfur pollution was cooling things down at the same time.
Exactly. You had these two competing forces. So the net effect on global average surface temperature was pretty small for a while. Until after about 1970. By then, greenhouse gases were accumulating even faster, and we started putting in controls on sulfur pollution, for acid rain and air quality reasons.
Right. Clean Air Acts and things.
Precisely. So that cooling effect from the sulfur aerosols started to diminish, while the warming effect from CO2 kept growing. And that's when you see the really marked temperature increase starting after 1970.
Wow. It's like we took the brakes off, in a way.
In a sense, yeah. We removed one pollutant that happened to be masking the effect of another.
Okay, let's talk about where all this extra heat is actually going, because it's not just staying in the air, right?
Yeah.
The oceans play a huge role.
Oh, massive. It's actually mind-boggling. The oceans have absorbed something like over 90% of the extra heat trapped by greenhouse gases.
90%.
Over 90%, yeah. This makes tracking the ocean's heat content a really crucial indicator of climate change, maybe even more so than just air temperature sometimes.
Why can they absorb so much?
Well, water just has a much, much higher heat capacity than air, about 1,000 times larger, actually. So the oceans can soak up an enormous amount of heat energy without their temperature shooting up quite as dramatically as the atmospheres would.
Okay, so they're like a giant heat sponge.
A massive heat sponge, exactly. But soaking up all that heat isn't without consequences, obviously.
Right. Which brings us squarely to sea level rise.
Yeah.
So is it just this ocean heating causing it, or are there other big factors?
It's both, really. There are two main drivers for the sea level rise we're seeing now. First, as you mentioned, is thermal expansion.
Yeah.
As the ocean water warms up, it literally expands, takes up more space, just like mercury in an old thermometer.
Mm-hmm.
And given the ocean has absorbed, like we said, roughly 90% of the Earth's extra heat over the last 40 years or so, that expansion adds up.
And this takes a long time.
A very long time, millennia, actually, for the full effect to work its way through the deep ocean. So the expansion we're seeing now is just the beginning. Based on the heat that's already been absorbed, there's more baked in, so to speak.
Wow. Okay, so that's one driver. What's the other big one?
The other big one is melting land-based ice. And it's important to stress land-based.
Right, not icebergs already floating. That doesn't change sea level much.
Exactly. We're talking about glaciers on mountains, ice caps, and especially the two giants, the Greenland ice sheet, the GIS, which holds enough ice to raise global sea levels by about 7 meters if it all melted.
7 meters?
Yeah. And then there's the West Antarctic ice sheet, the WAIS, which holds maybe another 3 to 5 meters worth.
Okay, those are huge numbers.
They are. And what's really interesting, maybe worrying, is that earlier IPCC reports, like the one back in 2007, their projections for sea level rise were actually considered pretty conservative, maybe even too low.
Why was that?
Well, at the time, scientists didn't fully understand the complex ways these massive ice sheets could actually lose ice. It wasn't just about slowly melting from the top down.
Ah, so like big chunks breaking off or meltwater getting underneath?
Exactly. Things like calving dynamics, marine ice sheet instability. These processes weren't fully incorporated into the models back then because the understanding just wasn't there yet. So those early estimates largely left out potentially rapid contributions from Greenland and West Antarctica.
Which means the potential for rise this century could be higher than those older estimates suggested.
That's certainly what the more recent science indicates, yes. The understanding of ice sheet dynamics has improved significantly.
Okay, this is fascinating, but how do we actually measure this rise? It seems like it would be hard to track tiny changes across the whole globe. Is it just guesswork?
Oh, definitely not guesswork. We have pretty sophisticated methods now. Historically, the main tool has been tide gauges.
Like the ones you see in harbors.
Exactly. There are about 1,900 of them around the world, and their data is compiled by the Permanent Service for Mean Sea Level, the PSMSL. These give us really valuable long-term records, some going back centuries.
But there are issues with those, right? Like where they're located.
There are. They're definitely concentrated more in the northern hemisphere historically, and the big challenge is correcting for local land movement.
What do you mean? The land itself moves?
It does. Think about it during the last ice age. Huge, heavy ice sheets pushed down the land underneath them.
Right.
Now that the ice is gone, the land is slowly bouncing back up. It's called glacial isostatic adjustment, or GIA. So in some places, like Scandinavia or parts of Canada, the land is rising. A tide gauge there might show sea level falling relative to the land, even if the global average sea level is actually going up.
So you have to mathematically remove that effect.
Precisely. You have to account for GIA and other vertical land movements like subsidence from groundwater withdrawal to get an accurate picture of the actual ocean water level change from tide gauges. It's complex.
Okay, so tide gauges give us the long history, but with caveats. What's the modern approach?
That's where satellite altimetry comes in. Since about 1993, we've had satellites orbiting the Earth specifically designed to measure the height of the sea surface very precisely using radar pulses.
And these cover the whole globe.
Pretty much the whole globe, yeah. They give us a much more uniform and detailed picture of global mean sea level, or GMSL.
And what are the satellites telling us? How does it compare to the older projections?
Well, the rate of GMSL rise measured by satellites since 1993 has actually been at the upper end of what those earlier IPCC projections suggested.
Really?
Yeah. For example, the data shows that between 2014 and 2023, the rate was about 4.8 centimeters per decade.
Okay, 4.8 centimeters.
Yeah.
Almost 5 centimeters a decade. For some people listening, that might not sound like a huge amount year to year. Can you put that rate into context? What does that actually mean for a coastal city over, say, 50 or 100 years?
That's a really important point. While 4.8 centimeters, or just under 2 inches per decade, might seem small if you think about it annually, it adds up relentlessly. Over a century, that's nearly half a meter, close to 20 inches. Now imagine you live in a low-lying coastal area or on a small island. Even just a few extra inches of sea level height dramatically increases the risk and severity of flooding during high tides, and especially during storm surges. What used to be a rare flood event becomes much more common. It makes coastal defenses less effective, so that seemingly small rate translates into significantly increased risk over time.
Gotcha. That makes sense. But you mentioned natural variations earlier affecting temperature. Do those affect sea level measurements too? Like El Nino?
Yes, absolutely. Natural climate patterns definitely cause short-term ups and downs in the global mean sea level. El Nino is a great example. During strong El Nino events, like the big one in 1997-98, global sea level can temporarily jump up because rainfall patterns shift, putting more water over the oceans versus land.
And La Nina does the opposite.
Generally, yes. La Nina conditions can lead to a temporary dip in GMSL, like we saw around 2008. There are also longer-term oscillations, like the Pacific Decadal Oscillation, PDO, or the North Atlantic Oscillation, NAO, that can influence sea level trends over decades.
So the graph isn't just a smooth upward line.
No, not at all. If you look at the year-to-year data, it bounces around quite a bit because of these natural variations. The key point, though, is that underneath all that natural noise, there's this clear, accelerating, long-term upward trend. That underlying trend is what's driven by human-caused climate change.
Okay, so we have the main drivers, thermal expansion, melting land, ice, and we can measure the rise, separating out the natural wiggles from the long-term trend. Are there any other factors that can mess with sea level, maybe just locally?
Yeah, definitely. Tectonic activity is one. That massive earthquake off the coast of Japan in 2011, for instance. It caused parts of the coastline, like the Ojika Peninsula, to suddenly sink or subside by over a meter. Locally, that's like an instant, massive sea level rise.
Wow.
And then there are human activities that cause the land itself to sink. Pumping out huge amounts of groundwater is a big one in some areas.
Like for cities or agriculture.
Exactly. Places like the Ganges Delta in Bangladesh and India, or the Char Phraya Delta where Bangkok is located.
Okay.
Studies showed that between the 1960s and 1990s, the land there was subsiding by up to 17 millimeters per year in some spots due to groundwater extraction. That's way faster than the global sea level rise rate. So for those specific locations, the relative sea level rise they experience is much, much worse because the land is sinking at the same time the ocean is rising. It's a double whammy.
That really compounds the problem for coastal communities. Okay, so we've got a good handle on the mechanics of measurement. Let's shift to the consequences. What are some of the most immediate environmental impacts we're seeing or expecting?
Well, one of the most visible ones is definitely beach erosion. It's already happening worldwide, but sea level rise just makes it worse.
How so?
Because as the water level gets higher, waves can reach and attack parts of the beach and dunes that were previously stable, especially during storms. It basically shifts the whole erosion process further inland.
Any examples that stand out?
There was a pretty striking study from Japan back in the 1990s. They estimated that with about 30 to 100 centimeters of sea level rise, which is well within the projections for this century, anywhere from 57% to potentially 90% of Japan's existing sandy beaches could be lost.
90%.
Potentially, yeah. with shorelines retreating maybe 25 meters on average. Now, apparently, the average width of a sandy beach in Japan is only about 30 meters.
So they could basically disappear.
In many places, yes. Imagine losing nearly all of your country's sandy beaches. It's not just about tourism or recreation. Beaches are also natural coastal defenses. Losing them is a huge environmental and economic blow.
That's a stark image. What about other types of coastal ecosystems, marshes, mangroves?
They're also highly vulnerable. Ecosystems like salt marshes, tidal flats, mangroves, they're incredibly important habitats and also provide coastal protection.
But they can adapt to some sea level rise, can't they, by building up sediment?
They can, up to a point, but they face a couple of big problems now. One is often a lack of sediment supply, maybe because rivers are dammed upstream. The other big issue is what's called coastal squeeze.
Coastal squeeze.
Yeah. As sea level rises, these ecosystems naturally want to migrate inland to higher ground. But often there's a seawall or a road or buildings right behind them.
Ah, so they have nowhere to go.
Exactly. They get squeezed between the rising sea and human development, and eventually they can just drown. We're already seeing this happening, for instance, with mangrove forests retreating in parts of Thailand, partly due to that land subsidence we talked about, which acts like local sea level rise.
And coral reefs. They're already stressed by warming.
Right. Hugely stressed. Coral reefs are incredibly sensitive to temperature. Just a 1 to 3 degrees Celsius increase in seawater temperature can trigger widespread coral bleaching, where the corals expel the algae living in them and turn white. If the stress lasts too long, they die. And since sea level rise is driven by the same warming that causes bleaching, it's another stressor. Healthy reefs can sometimes grow upwards to keep pace with slow sea level rise, but stressed, bleached reefs often can't. Losing reefs means losing vital habitat for fisheries and losing critical natural breakwaters that protect coastlines.
So the environmental impacts are widespread. What about the direct hit on people, on our health, our resources, our homes?
The impacts on human well-being are definitely profound. One major issue is water scarcity and quality.
How does sea level rise affect fresh water?
As the sea level pushes higher, salty ocean water can intrude further up into river estuaries.
Okay.
And maybe more critically for many communities, it can seep into coastal aquifers, the underground layers of rock and soil that hold fresh groundwater.
Contaminating drinking water supplies.
Exactly. This saltwater intrusion can make wells unusable. It's a huge problem, especially for small island nations that rely heavily on thin lenses of fresh groundwater floating on top of denser saltwater.
Is there data on that?
Yeah, there was an estimate for Kiribati, a low-lying Pacific island nation. It suggested that just a 50-centimeter sea level rise, combined with a potential 25% reduction in rainfall, could shrink their main freshwater lens by over 60%.
60%? That's devastating.
It really threatens their very existence. Imagine your primary source of fresh water just disappearing or becoming too salty to drink.
And you mentioned earlier how the land itself can be affected.
Right. Higher sea levels mean the water table, the level of groundwater under the surface also rises.
Okay.
This affects the stability of the ground itself. For instance, during an earthquake, soil that's saturated with water is much more prone to liquefaction.
Where it turns to liquid.
Basically, yeah. The soil temporarily loses its strength and structure and behaves like quicksand. This can cause buildings to tilt or sink and underground pipes and cables to break. It also reduces the load-bearing capacity of the ground, which can undermine foundations, river dikes, seawalls, critical infrastructure. A study looking at Tokyo Bay found that the combination of sea level rise and potentially higher river levels significantly increased the predicted risk of liquefaction in future earthquakes.
That's a hidden danger you might not immediately think of. What about the most direct impact, just plain flooding and inundation?
Yeah. That's obviously the big one. The risk of coastal inundation, especially during storms, is increasing dramatically.
Do we have numbers on how many people are currently at risk?
Globally, the estimate is around 270 million people currently live in areas that are vulnerable to what's called a 1-in-100-year coastal flood event, basically. A flood level that has a 1% chance of being exceeded in any given year.
270 million. That's already a huge number.
It is. And the projections for 2100 are really sobering. Without significant investment in new coastal protection, that number could rise to something like 670 million people at risk. Even with enhanced coastal protection measures, the estimate is still around 450 million people at risk by 2100 under moderate to high emission scenarios.
And where are most of these vulnerable people located?
The vast majority, about 80%, are in the Asia and Pacific region.
Why there specifically?
It's a combination of factors. You have densely populated mega deltas like the Ganges Brahmaputra or the Mekong. You have huge coastal megacities, Tokyo, Shanghai, Mumbai, Jakarta, many others. And of course, you have numerous low-lying, small island developing states that are incredibly vulnerable.
Any specific projections for a developed country, like Japan again?
Yeah, that same Japanese study projected that by the 2090s, depending on the scenario, somewhere between 63 and 72 square kilometers could face regular inundation. That would put 300,000 to 350,000 people at direct risk, with potential economic damages in the range of 1.8 to 2.3 trillion Japanese yen.
Trillions.
And crucially, they found that many existing seawall designs would likely become insufficient to handle the higher sea levels and potentially stronger storms.
Which raises a huge question about how we protect these places.
Yeah.
And inevitably, this must lead to discussions about people having to move, right? Climate migration.
Exactly. All these impacts, loss of land, loss of fresh water, increased flooding, damage to infrastructure, they inevitably raise the prospect of large-scale human migration, both within countries and potentially across borders. And this ties into issues of climate justice and inequality. Often, the communities most vulnerable to sea level rise are poorer coastal populations or people in developing nations who have contributed the least to the greenhouse gas emissions causing the problem in the first place.
Right. And they often have the fewest resources to adapt or relocate.
Precisely. So it exacerbates existing inequalities and creates this real moral dimension to the challenge. It's not just an environmental problem, it's a profound social and ethical issue too.
Okay, so we've laid out the problem, the science behind it, and the really serious impacts. Now, the crucial part, what can we actually do about it? How do we chart a course forward?
Well, broadly speaking, the responses fall into two main categories: mitigation and adaptation.
Okay, mitigation and adaptation. Let's break those down. What's mitigation?
Mitigation is all about tackling the root cause. It aims to stabilize the climate system itself by reducing the emissions of greenhouse gases going into the atmosphere.
So stopping putting more fuel on the fire.
Exactly. And also, potentially, enhancing the removal of greenhouse gases already there, for instance, through planting trees or developing carbon capture technologies. The goal of mitigation is basically to avoid the situation becoming completely unmanageable in the future.
Okay, avoiding the unmanageable. And adaptation.
Adaptation is about dealing with the impacts that are already happening, or the ones that we know are now unavoidable, even if we do mitigate successfully.
Right, because as you said, some changes are already locked in.
Correct. So adaptation involves adjusting our societies, our economies, our infrastructure to the current or expected changes in climate and their effects. This could mean things like improving early warning systems for storms, developing drought-resistant crops, building seawalls, or changing land use planning in vulnerable areas. It's about preparing for the unavoidable impacts.
Got it. So mitigation tries to limit the problem. Adaptation helps us cope with what we can't avoid. Let's dig into mitigation first. What are the key practical steps there?
A huge one, probably the biggest, is the clean energy transition. There's really widespread scientific and increasingly political support for phasing out fossil fuels as quickly as possible by doing two main things. First, conserving energy, just using less of it wherever possible. And second, switching our energy supply to clean sources that don't produce significant carbon pollution.
Like wind and solar.
Exactly. Wind, solar, hydropower, geothermal, and also nuclear power in some scenarios. The uptake of renewables has been accelerating dramatically, actually. One stat mentioned was that renewables represented something like 86% of all new electricity generation capacity installed globally in 2023.
86%, that's huge.
It is a very positive sign, but the overall energy system still relies heavily on fossil fuels, so the transition needs to happen much faster.
And you mentioned energy conservation too, that's just as important.
Absolutely crucial. Reducing overall energy demand makes a transition to clean energy easier and cheaper. If we need less energy overall, we don't have to build quite as much new clean energy infrastructure.
Where can we save energy?
Across all sectors, really. In transport, shifting to electric vehicles, promoting public transit, cycling, walking. In buildings, better insulation, energy-efficient appliances, using heat pumps instead of furnaces or boilers. In industry, improving process efficiency. It all adds up.
Okay. What about other sectors like agriculture and heavy industry? They're big emitters too, right?
They are, and they present different challenges. In agriculture, shifting dietary patterns is a big one. The sources mention that moving towards more plant-based diets could significantly cut emissions, noting that eliminating meat and dairy production could potentially reduce emissions from agriculture and related land use by about 3/4.
Wow, 3/4. That's massive.
It highlights the impact of livestock farming. For heavy industry, like producing steel and cement, it's trickier because their emissions often come from the chemical processes themselves, not just burning fuel.
So what's the solution there?
A lot of research is going into developing alternative chemistries and processes, using hydrogen as a fuel or feedstock, and implementing carbon capture on industrial facilities. But these are still mostly under development or expensive.
Which brings us to carbon capture. And also removing CO2 that's already out there. CDR.
Right. Carbon dioxide removal, CDR strategies, aim to actively pull CO2 out of the atmosphere. This can range from natural approaches like reforestation or changing farming practices to store more carbon in the soil that's sometimes called carbon farming.
To more technological solutions like direct air capture, DAC machines that suck CO2 out of the air, or carbon capture and storage, CCS, fitted to power plants or industrial sites.
How effective is CCS currently?
Well, the source material notes that currently CCS removes only a tiny fraction, about 0.1% of annual global greenhouse gas emissions. So while it might play a role, its current scale is very limited compared to the size of the problem.
Okay. There's one other mitigation idea sometimes mentioned, solar radiation modification, SRM. That sounds pretty sci-fi.
It does sound sci-fi, and it's quite controversial. SRM, or solar geoengineering, refers to proposals to deliberately reflect a small amount of sunlight back into space to cool the planet.
How would you even do that?
The most discussed method involves injecting reflective aerosol particles, maybe sulfur compounds, into the stratosphere, mimicking the cooling effect of large volcanic eruptions.
Sounds risky. It carries potentially significant risks, yes. One major concern is the so-called termination shock. If you started doing this and then suddenly stopped, the planet could warm very rapidly. There are also concerns about unpredictable side effects on weather patterns, and it does absolutely nothing to address the root cause of CO2 buildup or related problems like ocean acidification.
So it's not a magic bullet.
Definitely not. Most scientists see it, if at all, as a potential supplement to deep emissions cuts, not a replacement. And there are huge governance questions around who would control it and how. It's a very complex topic.
Okay, so that covers mitigation, cutting emissions, cleaner energy, maybe some CDR. Now, let's turn to adaptation. How do we prepare for the sea level rise that's already coming?
Right. For coastal adaptation specifically, the IPCC has outlined 3 main strategies. They call them protection, accommodation, and retreat.
Okay, protection, accommodation, retreat. What's protection?
Protection is basically defending the land from the sea using engineered structures. Think seawalls, dikes, levees, breakwaters, storm surge barriers. Hard infrastructure.
Building walls higher.
Essentially, yes. Protecting valuable assets, cities, critical infrastructure.
Okay. Accommodation.
Accommodation means continuing to live and work in coastal areas, but changing how we do it to cope with higher water levels and flooding. This could involve things like raising houses up on stilts or pilings, designing buildings to be flood-proof on lower levels, switching agriculture to more salt-tolerant crops, or having better warning systems and evacuation plans.
So learning to live with the water sometimes.
Exactly. Adjusting practices rather than just holding the water back entirely.
And the third one, retreat. That sounds pretty drastic.
It can be, yeah. Retreat, or sometimes called managed realignment, involves strategically moving people, assets, and activities away from the most vulnerable coastal areas. This could mean things like zoning regulations that prevent new construction in high-risk zones, offering buyouts for properties that repeatedly flood, or physically relocating entire communities over time.
That must be incredibly difficult socially and politically.
Extremely difficult. But in some low-lying areas or places facing very rapid erosion or subsidence, it might eventually become the only viable long-term option.
You mentioned earlier that after big disasters like Katrina or the Indian Ocean tsunami, there was maybe a renewed focus on protection, building bigger walls.
Yeah.
Is there a tension between that and more nature-based solutions like restoring mangroves or wetlands?
That's a really good point. There was definitely a period where those catastrophic events highlighted the limitations of existing defenses and led to calls for and investments in stronger hard protection, especially for major cities and critical facilities. But at the same time, there's been a growing appreciation for ecosystem-based adaptation using natural features like mangroves, coral reefs, dunes, and marshes to buffer coastlines. These often provide multiple benefits beyond just flood protection, like habitat and carbon storage.
So it's not necessarily either?
Increasingly, the thinking is that it's not. The best approach often involves a combination, maybe a seawall, combined with a restored marsh in front of it. It depends very much on the local context, the level of risk, the assets being protected, and the costs. But yes, robust protection structures are still seen as essential in many high-value, high-density areas, even while ecosystem approaches are prioritized where feasible.
What about infrastructure that's not right on the coast but could still be affected, like bridges, roads, power plants, maybe further inland but near rivers?
Yeah, adaptation needs to consider those too. This involves the concept of climate-proofing infrastructure, meaning designing and building new infrastructure or upgrading existing infrastructure to withstand the future climate conditions it's likely to face, including higher sea levels, more intense rainfall, higher temperatures, etc.
So building bridge supports higher, using different materials.
Exactly. It might mean a higher initial cost to build something more robustly, but the idea is it could save a lot of money in the long run by avoiding damage or failure later on.
And for stuff that's already built.
For existing infrastructure, it often involves what's called a stepwise strengthening approach. You might not rebuild everything immediately, but you assess the increasing risk over time and plan upgrades or reinforcements in stages as needed.
And all of this protection, accommodation, retreat, infrastructure needs to fit together.
Absolutely. That's where integrated coastal management, or ICM, comes in. It's about looking at the entire coastal zone as a system. The environment, the economy, the communities, and developing adaptation plans holistically, not just piece by piece. It's about finding ways for human activities and the natural environment to coexist sustainably in the face of climate change.
Okay, that makes sense. Let's zoom out again to the global picture. How are countries actually working together, or maybe failing to work together on this?
Yeah.
We've had international climate talks for decades now.
We have. The International Response Framework really started with the UNFCCC, the United Nations Framework Convention on Climate Change, back in 1994. That set the overall goal: prevent dangerous human interference with the climate system.
Okay, the umbrella agreement.
Right. Then came the Kyoto Protocol in 1997. That was significant because it included legally binding emission reduction targets, but primarily for developed countries.
The U.S. famously didn't ratify that one.
Correct, which weakened its overall impact. Then fast forward to 2009, the Copenhagen Accord. That aimed to keep warming below 2 degrees Celsius and also proposed the Green Climate Fund to help developing countries adapt and mitigate.
But it didn't quite live up to expectations.
It was seen by many as falling short, yeah. The commitments weren't legally binding in the same way, and the funding goals for the Green Climate Fund weren't fully met by the 2020 target.
Okay, then the big one, Paris 2015.
Right, the Paris Agreement. That was a landmark because almost every nation on Earth signed on. They agreed to collectively keep global warming well below 2 degrees C compared to pre-industrial levels and pursue efforts to limit it to 1.5 degrees C.
And countries set their own targets, right?
Yeah.
The NDCs.
Exactly. Nationally determined contributions. Each country puts forward its own plan. The issue is, when you add up all the current NDCs, they're still not ambitious enough. The projections suggest they lead to warming of around 2.8 degrees C by the end of the century.
So a big gap between the Paris goals and current national plans.
A significant gap, yes, which is why there's constant pressure for countries to increase their ambition.
Is there any international environmental agreement that's seen as a real success story, maybe something we can learn from?
Actually, yes. The Montreal Protocol from 1987.
Because about the ozone layer, right? CFCs.
Exactly. It was designed to phase out chemicals like chlorofluorocarbons, CFCs, that were destroying the ozone layer, and it worked incredibly well. But here's the fascinating part. Those same ozone-depleting substances were also extremely potent greenhouse gases, thousands of times more powerful than CO2 in some cases.
Oh, wow. So phasing them out helped the climate, too.
Massively. By phasing out CFCs and related chemicals, the Montreal Protocol inadvertently became arguably the single most effective climate mitigation treaty to date. Estimates suggest it might have prevented an additional zero point 0.5 to 1 degrees Celsius of warming that we would have otherwise seen.
More effective than Kyoto?
Potentially, yes, in terms of greenhouse gas emissions avoided so far. Yeah. And then the Kigali Amendment was added to the Montreal Protocol in 2016 to specifically phase down HFC's hydrofluorocarbons, which were introduced as replacements for CFCs, but are also potent greenhouse gases.
So it shows that global cooperation can work when the science is clear and there's political will.
It's a really powerful example of success, absolutely.
Okay, beyond the international treaties, what are individual countries or regions doing? Any examples of strong national action?
Yeah, we are seeing significant action in some places. The UK Parliament, for example, declared a formal climate emergency back in 2019, which signaled a high level of political concern. The European Parliament followed suit. And the European Green Deal is a really ambitious package from the EU. It sets a legally binding target for the EU to be climate neutral net zero emissions by 2050.
And specific policies.
Lots of them. For example, one concrete target is that all new cars sold in the EU from 2035 must be zero-emission vehicles. That's a major push towards electric mobility. So yes, national and regional actions are crucial alongside the global agreements.
But even with these agreements and national actions, there's this other force at play. Climate change denial and the spread of misinformation. The sources mention this quite a bit, even comparing the tactics to the tobacco industry playbook. How big of a problem is this?
It's been a significant obstacle, unfortunately. The sources describe how organized campaigns, often funded by vested interests, have actively worked to manufacture doubt about the science, minimize the seriousness of the impacts, or exaggerate the costs of taking action. This strategy, which did indeed echo tactics used by the tobacco industry to obscure the links between smoking and cancer, originated largely in the United States but has spread globally.
And it's not just denying warming exists anymore, right? It's more nuanced now.
Exactly. Outright denial, it's not happening, is less common now among influential actors. The focus has often shifted to what some call discourses of delay. This can involve questioning the human contribution, arguing it's mostly natural cycles, downplaying the future impacts, it won't be that bad, emphasizing the costs of climate action, it's too expensive, or suggesting it's too late anyway, or that technological fixes will magically appear.
All designed to slow down policy changes.
Precisely. By creating a sense of manufactured controversy or uncertainty, even when the scientific consensus is overwhelming, over 99% of climate scientists agree humans are the main driver. It provides cover for inaction or delays meaningful policy responses.
How does this affect what the public thinks? Do people realize how strong the scientific consensus is?
Generally, no. Studies consistently show that the public significantly underestimates the degree of scientific agreement on human-caused climate change. That perception gap is likely fueled, at least in part, by these misinformation campaigns.
But are people worried? Is concern growing?
Yes, concern has generally increased over time globally. That 2024 survey you mentioned earlier, across 125 countries, found a huge majority, 89%, saying they want stronger political action on climate change.
89%. That's almost everyone.
It's a massive number. But interestingly, the same survey found that people consistently underestimate how many other people in their country share that desire for action.
Huh. Why is that?
It might be what's called the spiral of silence or pluralistic ignorance. People might privately hold strong views but assume they're in the minority, perhaps because the loudest voices in the media or politics don't always reflect that majority concern. This underestimation of shared concern can actually hinder collective action because people might feel less empowered or more isolated.
So, if people are concerned, how is that translating into action? Beyond just answering surveys.
We're definitely seeing a growing and diversifying climate movement around the world.
Like the school strikes.
Exactly. Public demonstrations, the school strikes inspired by activists like Greta Thunberg, acts of civil disobedience targeting fossil fuel projects, or government inaction. These are becoming more common. And another really significant avenue is climate litigation. Activist groups, and sometimes even individuals or local governments, are increasingly suing national governments to force them to adopt stronger climate policies, or suing fossil fuel companies seeking compensation for climate-related damages.
So using the legal system as a tool for change.
Yes. It's becoming a really important front in the push for climate action, holding governments and corporations accountable through the courts. It's a dynamic and evolving landscape.
Okay. So bringing this all together, what does this mean for you listening right now? We've seen that human activity is well, unequivocally driving climate change and sea level rise. The impacts are real, they're global, and they hit vulnerable communities hardest. But we've also explored the solutions, the pathways for mitigation through things like clean energy and the strategies for adaptation like protection, accommodation, retreat. And there's a very strong scientific consensus backing this up, and it seems growing public demand for action.
But there's a final point that's really crucial to grasp, something sobering from the science. Because of the inertia in the climate system, especially the oceans and ice sheets, even if, hypothetically, we stopped all greenhouse gas emissions tomorrow, dropped to net zero instantly, sea level rise would still continue for centuries.
Wow, so it's already baked in.
A significant amount of future rise is already locked in due to the warming that's already occurred. The oceans will continue to warm and expand for a long time, and the ice sheets will take centuries, maybe millennia, to fully respond to the temperature changes we've already caused. It's like trying to stop a massive supertanker. You can cut the engines, but its momentum carries it forward for a very long way.
So the truly sobering takeaway here is that our actions now aren't about stopping sea level rise entirely in our lifetimes or even our children's lifetimes. It's about deciding how much rise we're committing future generations to, how fast and how high the water ultimately gets.
Precisely. We can influence the trajectory significantly, but we can't just turn it off.
Which leaves us with a pretty powerful thought, doesn't it? Given this locked-in future rise, this commitment playing out over centuries, what does that really imply for how we plan our cities, how we innovate, how we manage coastlines, and, maybe most importantly, how we think about our responsibility to generations yet to come? That's something to really mull over.